Hey guys, Assalamualaikum. Welcome to today's notes. First, I want to draw your attention to the bit in yesterday's notes where we talked about the perpendicular bisector. And before we start today's notes, I just want to recap that. Remember, we talked about a perpendicular bisector making that perfect 90-degree angle and then bisecting the side and cutting it in half so that this piece was the same as this piece. And when that happened, if we extended the perpendicular bisector, remember that I made a note that it wouldn't necessarily hit up the vertex of the opposite side, on the opposite side of this triangle. So if you kept drawing the perpendicular bisector, it wouldn't necessarily hit that vertex B right here. So it turns out that we'll look at today where if we only cared about the bisector bit, so if we only cared about drawing a line that cut AC in half, but we didn't care so much about the perpendicular part of that, we could essentially draw a line from the middle of AC to the vertex. And that is what we would call a median. So now we're going to start with today's notes. So I'm going to write out the definition of a median first, and then I'll explain here on the side. So a median of a triangle is a segment whose endpoints are a vertex of whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So if you look here, this red line is considered a median because it has two jobs. One, it cuts the side AB perfectly in half because this segment is the same as this segment. And so it starts at the midpoint of AB and then it ends up at the vertex of the opposite side, the vertex of the triangle named C. Every triangle will have three medians because we can do it to this side as well. We can look at cutting AC in half and finding the midpoint somewhere where this piece will be the same as this piece, and we can start at the midpoint and end up at vertex B. And then we can do the same thing on this last side and say, okay, here's the middle, this is the same as this, and then I can start at that midpoint and end up at that vertex. It's not very straight, but you get my idea. What's cool is that if you draw out the three medians of a triangle, they're all going to meet at one place. And if you remember, we call those three lines being three lines that are concurrent. So the point of concurrency of the medians, the three medians of the triangle, is called the centroid of the triangle. So that point right there would be called the centroid. So unlike the circumcenter of a triangle that we looked at yesterday, our centroid will always be on the inside of the triangle. And the centroid is cool because it's also called the center of gravity. And it's given this name because it is the point where a triangular region will balance. So if I held up my pen like this and I place this triangle on my pen right at that centroid, that triangle will balance on my pen and won't fall off. Okay, so now we talk about our centroid theorem right here in the middle of the page. And what it's saying is that if I look at my median, so from A all the way to Y, there's one of the medians, okay? It tells us that the centroid of a triangle, so right here, P, is located exactly 2/3 of the way from the vertex of the midpoint of the opposite side. So all that means is if I look at from A all the way to Y, my median, okay, then this theorem tells me, so here's AY, it talks about it right here. It tells me that from A to P is 2/3 of the way from A all the way to Y. And the same thing happens for the other medians as well, that from B to P, it's going to be 2/3 of the way of going from B all the way to Z. And the same thing happens for this last side, that from C to P is 2/3 of the way of going from C all the way to that midpoint right there, X. Okay. Okay, now we've arrived at our last big definition. So we have to kind of build up to it. An altitude of a triangle is a perpendicular segment from a vertex to the line containing the opposite side. And I'll explain that in a minute with a picture. Every triangle has 3 altitudes. An altitude can be inside, and we'll see that an altitude can happen outside, or it can happen literally on the triangle. Okay, so I'm gonna put a blank triangle over this so that you can kind of see how they got this picture. You don't have to do this. Okay, so if I find the altitude of this triangle starting from the vertex Q, I am dropping a line from this vertex to the opposite side and trying to make 90 degrees. So if I grab my handy dandy corner of a paper again, I can see exactly where a line will make 90 degrees with this side RS. So I want to slide it right until this line I create will hit Q, start at Q, go down to this side RS, and hit at a 90-degree angle. Okay, and what we will see is if I do it to this first vertex Q, my altitude happens to be inside my triangle. So that's what the first blank says here. In triangle QRS, the altitude QY is inside the triangle. But if I do it to the vertex R, what we will see is that if I try to drop a line from R to QS, it's really weird because you won't be able to get like perfectly 90 degrees. Like if you lay this orange sheet flush along the side QS, you see that's how it gets 90 degrees. But the top of this paper is not hitting R unless you scooch it all the way outside of the actual triangle. And you have to also imagine an invisible line extending off the side of QS. So let me go ahead and create the invisible side first. So here's QS. It actually stops here in the actual triangle. Imagine it going further invisibly. Then I can easily say, okay, I get 90 degrees when I'm along this edge QS, 90 degrees, 90 degrees, 90 degrees, keep going, and I want this line that's creating 90 degrees to end up hitting the vertex R. So once you position it correctly where the edge of the paper is touching R, but then when I drop it down, it's going to make that 90 degrees. There's my altitude. And then if I do the same thing with the last vertex S, so let me turn the paper around so you can see. I want to drop a line from S to hit at this side, RQ. Don't look at the blue line because that's not actually part of our real triangle. This is our actual triangle. I want the line to drop from S and hit 90 degrees at QR. It's not going to happen if it's inside the triangle. So I actually have to do the work of extending out my last side of the triangle, imagining it's invisible side extending this way. Then I can find the altitude where, so I'm using the corner of the page to make 90 degrees with the green line. And the top of my paper needs to hit at vertex S. Right there, This would be my last altitude because it makes 90 degrees with this side of the triangle, and it starts at the vertex. So that's what this next line talks about, that Rx and SZ, which if I take away the sticky note, you'll see them labeled correctly. But in our picture, it's the blue one and the green one. The blue altitude and the green altitude are not inside the actual triangle right here, okay? And so they want you to notice that the lines containing the altitudes. So this blue line, this pinkish purplish line, and this light green line, if you extend them, they will be concurrent, meaning if you think back to our definitions from the last video, it means that they will eventually touch. So if I extend out this green line and I extend out this blue line, this blue altitude from vertex R, and I extend out the pink purplish altitude for Q, even though it was inside the triangle, I can extend it outside. If I did everything right, it should hit up at one point, showing that they're concurrent. And they labeled it P in the picture underneath. And the name that we give this point where all three altitudes meet is called the orthocenter, okay? And we will practice more examples in class.